Ramires, and I just started working with Piers Coleman on this new material called this beta phase or ytterbium aluminum boron 5 that we call YbAIB4. So I will start telling you what are the general properties of these materials, then telling you what this ESR technique measures, and why we have an unusual signal in this material in ESR. Then I'll introduce the key ideas to understand this unusual signal. And then we see that we need a model with an emergent hybridization to explain that. And after that, I will show you the results and conclusions and open questions. So in YbAIB we have 3+ ytterbium ions. So we have 4 F electrons, very localized electrons. And this material has a very funny structure and an interesting phase diagram. It's superconductor at very low temperatures and field with a very low TC and VC. And it shows a non-ferroelectric behavior at low temperatures, and if you don't have any magnetic field. And as soon as you apply a magnetic field, you can tune this material to the ferroelectric behavior. So this is the structure. It's quite interesting. Here is the unit cell. And we see here the ytterbium atoms in a smashed hexagonal lattice. And it sits in between 2 layers of boron atoms. These green ones here. So there's one here and one at the top and the bottom. And it sits in the middle of a 7 boron atom rings. We have also aluminum atoms in a deformed rectangular structure. But it turns out that this local 7-fold symmetry is quite okay, so ESR, so probably many of you know that ESR measures the following. So if you have your energy levels and you apply a magnetic field, you can Zeeman split your energy levels. And if you apply RF radiation in the system, you can tune this external field in such a way that you can get a resonance of the energy of the radiation with the energy of the Zeeman splitting. So here is the absorption line in terms of field with respect of the applied field. So you can tune your field and then you see a peak in your absorption. And usually the experiments, they show the derivative of this signal, and I don't know exactly what's the reason for that. Okay, so now the electron spin resonance in this material, why is it unusual? So we have at high temperatures this line shape, there's a Dysonian, and if you go to low temperatures, we start seeing hyperfine peaks below 10 Kelvin. We also see a shift in the ferromagnetic ratio, going from 2 at high temperatures to 3 at very low temperatures. There is the ferromagnetic ratio of these 4 F electrons that we have. We also have a big anisotropy at low temperatures, the black dots, in comparison with no anisotropy at high temperatures. And the unusual part comes with the intensity, that are these black dots here. So you can see that the intensity does not change with temperature. But I want to explain now why is it unusual. So let's compare what happens to the same system, changing ytterbium and putting in its place lutetium that has a full F shell, so it has no local lines. In this case, we don't see the hyperfine lines at low temperatures. We don't see any anisotropy at low temperatures. We don't see the ferromagnetic shift. And we don't see also the shift, any change in the intensity of the signal with temperature. In contrast, for ytterbium ruthenium-2 silicon-2 that has local moments, we see a big change in this intensity at low temperatures. So in this material, as we have a long-filled F shell, we would expect that it would increase because it has a Curie-like susceptibility. And one can show that this intensity that is related to the integral of that line of absorption, it is related to the static spin susceptibility. So if my susceptibility goes like Curie-like, I would expect that this intensity would be the same. So the problem here is to explain why we have this localized behavior for the intensity and this conduction electron-like behavior for the intensity with this other localized electron characteristics. Okay, so let's look more carefully at this deuterium and what my electrons are doing. So as I said, we have 4 electrons, so my angular momentum is 3, and it's more than half filled, so my total angular momentum is 7 halves. So I can write my Ramires doublets respecting time universal symmetry, just seeing which, so in principle I can have any combination of these states, any A, B, C, D, and normalized. But it turns out that as I am in the 7-fold local symmetry, I cannot find any combination of the doublets that respect time reversal and the 7-fold rotation. So my ground state would be a pure angular momentum state. So we need to find which one is of those it is. So there's this work of Nevedonsky and Coleman a couple of years ago, and they do a detailed study on that. But here I'll show just a pictorial view of the situation. So if you notice, we have our deuterium ions here in the center, and they make almost 50 degrees with the atoms in the boron. So if I look at my angular momentum states that I can have, I can find my ground state because my ground state will be the one that hybridizes the most with this boron, this conduction electrons in this boron ring. So I can already split the half and 7 half because they will not coincide with the electrons here. So let's take a look at the 3 halves and 5 halves. So we notice that the angle that the 5 halves does coincides better with these boron rings than the 3 halves. So this will be my pure ground state. And this is one of the key ideas to solve this problem. Okay, so now, as I have a pure 5-half state, I'll show that my ESR cannot prove my F electrons. Because I have a radiation coming with this energy, and we know that a photon carries 1 unit of angular momentum. So it will not be able to flip my spin from -2 + 5 halves, because then I would need 5 units of angular momentum. And it will not be able also to excite my electrons, because my crystal field is much bigger than the energy that this photon is carrying. So what I need to do is just calculate the spin response function for the conduction electrons in this case, because my ESR experiment is not able to prove the localized electrons. What makes my problem much simpler compared to Abraham's and Wolf work for YRS, because there you don't have this special ground state, so you can flip everything and you need to calculate the spin response function for the conduction, the F electrons, and any mix of that you can get. So for that, in a sense, we propose an emergent hybridization picture as a main field of a quantum impurity model, where I have my conduction band, my F level, and my hybridization between them. And here I include the effects of my Zeeman splitting with my C-component frequency that is given by the ferromagnetic ratio, boron magneton times the external field. And GC is for the conduction electrons, that is equal to 2. And GF will be the conduction, the localized electrons with ferromagnetic ratio equal to 2.3 that can be calculated from the lambda factor. Okay, so I need to calculate the propagator for this for the C electrons hybridized with my F electrons. And with them I can calculate my spin response function. So we know that ESR proves the imaginary particle susceptibility. So from these we can get the line shapes. But here first I will focus on the gyromagnetic ratio. So we can get from the resonance condition, I can make my if the resonance condition is exactly the condition that my external frequency is equal to the energy of my external frequency is equal to the energy of the signal splitting. That would be mu b external field times an overall gyromagnetic ratio, that is this G effective here. That I can write in terms of this GC and GF. And Z is my renormalization factor that will be able to change with temperature if I minimize my free energy with respect to this hybridization that I introduced before. So if I do that, I can get the temperature dependence of my gyromagnetic ratio going from 2 to 2.8 at low temperatures. And I also can introduce here phenomenologically the anisotropy, because we know that the system is an Ising-like system with an easy axis of magnetization. So I can introduce this cosine theta here for the magnetization of my F electrons. So from that I can plot also the angular dependence, the anisotropy of my gyromagnetic ratio for different temperatures. Okay, I also can get I also can explain why this hyperfine structure appears. Because in these materials we have different isotopes of the terbium, and we have a small concentration of odd nucleons, nucleons with odd number of nucleons. And we have particular this terbium-171 with nuclear spin 1/2. So if we consider a multiple scattering of a single impurity from these spin centers, we can introduce the hyperfine coupling of the spin of these nucleons with the F electron spins, and we can rewrite an F electron propagator with this multiple scattering. So we can rewrite this in this way that is useful to see that I have essentially the bare F propagator with 2 extra terms that will give me 2 extra poles, shifting my resonance by an amount equal to the strength of this hyperfine coupling. And this peaks the intensity of this peak will be proportional to the concentration of this isotope. So with that, we can get these line shapes, and at low temperatures, we see that the peaks appear. Okay, now about the controversial temperature independence intensity. As I said in the beginning, we can show, starting from the Ramires relation, that the real part of my susceptibility is related to my imaginary part of my susceptibility. And if I change some variables, and if I consider my resonance narrow enough, I can show that the static part of the static susceptibility, the real part of the static susceptibility, is related to this intensity of my spectrum. And if I notice that my susceptibility is actually, as it is a susceptibility of the conduction electrons, I will not expect it to renormalize because it has this renormalized factor here, and these star quantities, they all have a Z factor on it. So essentially, if I analyze the static term, I don't have any renormalization of this. So it explains why I have this temperature independence intensity. Okay, so with this picture, I could put together these characteristics that are in this code are unusual to see it together in these measurements. So it could explain the G factor shift, the anisotropy, the appearance of hyperfine peaks at low temperatures, together with the temperature independence of the intensity. But there we are trying to work now. Mainly about this non-ferromolecular behavior, if it's really intrinsically quantum critical, or if why it's fine-tuned, because it seems that this critical field it's very close to zero based on experiments. They can say it's strictly zero, but it's inside the error of the experiments. And it turns out that this picture, this very naive picture of the ground state, is very important because we could explain the anomalous thermodynamic behavior in this non-ferromolecular region just with this special hybridization based on the spy path that will have nodes in the z direction. So it turns out to, in principle, it's a very naive approach, but it turns out to get from this. And that's what I'm saying.
Questions?
Yeah, that's probably a rather ignorant question, but did you say that this lattice has a sevenfold symmetry?
So yeah, I can say that the lattice itself has a sevenfold symmetry, but I can say that my etherians will feel like locally a sevenfold symmetry. So actually there was a more detailed study for this ground state that were done by Lewandowski. So I put this pictorial view of that, but it turns out that the ground state is actually a pure 5 hat. So the crystal itself is not a full sevenfold because this is not possible, but locally they have the 7 more limits around it. So it for sure has an important effect in the crystal field.
Other questions? I have a naive question. In this structure, is there just one Ethereum side, or is there different sides? All Ethereum has this strange environment?
Yes, so if you go back.
Only one side?
You mean one? So all the Ethereums are in the 7-ring environment. If that was the question.
Yeah, that's the question.
Which part of the phase diagram do you see the hyperfile?
So the hyperfine you see in the Lowton Kelvin, then a small magnetic field. So I would say that they see it in this region. Okay, so my zoom. Okay, so they're the Lowton Kelvin, but at fields of this order. So they're in the current equation. Yeah, they are in this. They are in the current form.
It's low temperature.
It's below 10 Kelvin that we see the hyperfine.
Is that what are these points?
So these points came from specific heat, and this from resistivity measurements. So actually, it's not. There are many lines that can. It's not really defined, but they have this crossover. Different measurements will be used in the lines.
This structure, does it have inversion symmetry?
I'm sorry?
Does it have inversion symmetry, this structure?
No, I don't think so.
I think we see this thing is inverted.
Yeah. Central symmetry.
I think the center of this hexagon inverted with respect to center.
Oh, yes.
Yeah, right. So free to pick a point, which is not inversion.
Okay.
I think it's central symmetry. The first Ethereum-based superconductor, which is known.
Yes, it's okay.
So that's right. That's the central symmetry. Not good for dynamics. TC is a 30 minute Any other question before the beach? So we start again at 6 o'clock.